Thank you, Felix. Thank you for the opportunity to present today one of our use cases, which is the digital twin for the optimization of a special waste rotary kiln incineration plant. My name is Martin Hammerschmied, and I'm from the research group of Industrial Plant Engineering and Application of Digital Methods. The name of the institute is quite more complicated, but we'll see, let us say, process engineering from TU Wien. The first two slides, I would like to give you an idea what is our main idea about digital twinning, and afterwards I would like to show you the use case. So in our research group, we are mostly dealing with experimental facilities. So we are trying to develop new technologies, new environmental friendly technologies in topics are CO2 capturing, biomass-based conversion processes, and much more. So the main idea for digital twinning is to evolve virtual representations together with the experimental facility along the life cycle. So for us, it's important that also the virtual representation intelligence increases with the process itself. And this along the whole life cycle from lab scale to commercial scale. And additionally, we have a look on a holistic optimization and evaluation approach, not only technical KPIs, also economical, ecological, and other aspects are in this framework. But now I would like to go more in an industrial use case because it's more the topic of the Annex 18. I would like to speak about a digital twin of a hazardous waste rotary kiln. We are trying to implement at Vienna, and this is for the optimization of the process performance of this commercial industrial plant. It is a cooperative research project, and the project lead is by Wien Energie, which is one of the biggest energy provider in Austria, and so especially in Vienna and surroundings. And the project partners are TU Wien, which is the academic partner, NRAC, which is an SME for process engineering simulations, and Cloudflight, which are experts in data analytics, cloud computing, and so on. So as you can see in the timeline, we're in the final phase of the project, and therefore I can show you something right now. The initial situation is that in Vienna, in Simmering, part of Vienna, 2 rotary kilns are stated, and these 2 rotary kilns burns 100,000 tons per year of hazardous waste with 7 input streams. So these 7 input streams are really dealing with very heterogeneous waste streams, and these are often toxic and hazardous. And therefore, it's not really doable to make a complete sampling and analyzing. So it's a kind of surprise what's coming in the rotary kiln, what makes the process control really challenging. There are much more challenges because there is not a continuous feeding of the waste, the batch feeding of these different input streams. On the right side, you can see a diagram which shows you the mass flow over the time from different input streams. So the colors are indicators for these different input streams, and it should only show you that there is a really different input mass flow over the time which the plant has to dealing with. With this batch feeding, there are coming up peak loads due to emissions, temperatures, ash melting, which comes often to downtimes and so on. But the biggest challenge is, as I already mentioned, is that the wastes are not completely sampled. We only know exactly the waste code of the waste streams, and everybody who has seen a waste code knows that there's not really much saying about the waste. It's just a textual description about it, like filter material, for example, which can be from activated carbon to silicate, everything, which means it's a quite huge difference in heating values, which is really important for the combustion. Therefore, we need a lot of knowledge about the combustion behavior, about the fuel, and this is quite really complex when you don't know what you do in the rotary kiln, and therefore the process control is more reactive than proactive. And with the digital twin, we would like go more to the proactive side. First of all, a short scheme of the rotary kiln. So we have 7 to 8 input streams. Why 8 now? Because pasty waste and waste oil will be fed together. But let's go up to the barrels. So there are 4 different solid input streams with the direct barrels, bunker waste, shredded barrels, hospital waste, and 4 liquid ones with the master batch, which is a mix of solvents, wastewater, waste oil, and pasty waste. This all will be fed together with the air in the rotary kiln and will be pre-burned in it, and afterwards post-burned in a secondary combustion chamber, and thereout a hot flue gas will be produced, which is here for the waste heat recovery boiler to produce an overheated steam for the steam turbine to produce in the end electricity and heat. Now, would like to explain you in the next slides what is the main idea of the digital twin. So first of all, we have the physical facility with the plant and its control system. Out of the control system, we get measurement data. This measurement data contains temperature profiles, pressure profiles, mass flows, gas analytics, and so on. And we can feed this measurement data to a physical-based simulation model. So this physical-based simulation model is based on Python and on a sequential approach. So the subsystems, as I showed you before in the scheme, will be solved separately, one after another. So first of all, the inputs for the rotary kiln will be fed into the solver of the rotary kiln, and the results go in the next subsystem, the solver of the post-combustion chamber, and so on. So back to the scheme, to the overall idea. So we have now this physical-based simulation model, which calculates based on the measurement data due to the overdetermined system, a time-dependent fuel mixture, which was fed into the rotary kiln. And on the other hand, we know about the wastes due to a database which is called the Berthold system, the delivery data and the feed rates, which will be fed into the rotary kiln. So in this database, there are waste codes. We know in what storage system the wastes are stored, which supplier delivered this waste, and what quantity. So therefore, we know due to the physical-based simulation, the time-dependent fuel mixture, and we know the time-dependent waste codes and quantity which will be fed into the rotary kiln. But as I already mentioned, the waste codes are not really an indicator for the combustion behavior. So we need one more database to combine these 2 approaches. And this is the fuel classification model. So what is a fuel classification model? With these 2 diagrams, I would give you a short insight in this. So we had a look on the last years of the database from the waste streams, and we figured out the most important waste codes and built it up a fuel classification database. In there, you find for each waste code minimum and maximum numbers of elementary analysis and proximate analysis. For everybody who's not that deep into fuel analysis, so elementary analysis means the composition regarding to carbon, hydrogen, oxygen, and so on. And the proximate analysis means the combination, how much fixed carbon is in the fuel combined to the volatile and the ash. But it's not that important. It should just show you that there is, for every waste code, which we know, time dependent, there is an area for the following data-based approach where the solver can arrange the input and can guess what it should be. Therefore, we will combine now this Berthold system and the fuel classification model over a database algorithm with the physical-based simulation results, and we get out a determination of the chemical compositions of the waste streams. So we can determine now by this combination the real chemical compositions of the historical feeded waste streams. First of all, we did some months ago some experimental runs with well-known input streams to parameterize this physical model, to fix some bugs and to parameterize some setting values in the physical model. And afterwards, we now building up a database for composition of input streams due to the analyzing of historical data. To come to a digital twin in the end, there is a three-step timeline. These 3 steps, you can say it's quite obvious that this first one is the digital model, the second one a digital shadow, the third one a digital twin. So first of all, and this is the goal for this project, that we develop a database with results of the data analytics from historical data. So this database and physical models are not connected directly now with the control system. So we get historical data and can build up with them defined elementary and immediate analysis for every input streams we have analyzed, and therefore we can connect the waste code and the supplier with these analysis values. And with this knowledge, we can go to the second step. So we can implement this database we can connect this database with the rotary kiln optimization, with the rotary kiln control system to optimize it, and to use this knowledge about recurring fractions for the process optimization. So this the second step would be a one-directional automatic data flow between the control system from the database to the controls, from the control system to the database, so a digital shadow, and can guide the plant operators and the waste management as support instrument. And in the third implementation stage, there will be the automation of the rotary kiln plant and the waste management. So when we know what combustion behavior have the most wastes, then it is quite easier to control the plant, and then we can also realize a closed loop control of the plant, and we can also plan better the waste deliveries. So when we know we have much high calorific wastes now, then we can mix them together with low calorific ones to have a good value in the middle, for example. And maybe this would be a huge outlook, but there could also be possible to make automatic planning of the waste deliveries. Yeah, when I speak about optimization of the plant, then I speak about the permanent monitoring of the plant, which gets possible due to the digital twin. We can reduce the oxygen content in the flue gas when we know the waste better, because there is quite a huge the oxygen content in the flue gas is now from a little bit about 13%, so it's quite a lot. and the reason is that you don't know what it gets inside, and it's quite a reserve in it. So when we can decrease this oxygen content, we can increase the efficiency by some percent points, and get out more heat and electricity. And when we reach a reduction of the temperature peaks and peak loads, then we can decrease the downtime of the kiln. And less downtime means less heating oil consumption for startup process, which has clearly a economic and ecologic point of view. And last but not least, the support and training of the plant operators gets possible because it's really challenging to operate such a plant. And yeah, if there is a new plant operator, it's going to be a chance to train him and support him by his starting. Yes, that's all, and I hope you got it all. It's quite a big topic. I don't know if you understood all right, but now I'm here for answer your questions if something is not clear.
Thank you, Martin. This is indeed a very complex topic that you're dealing with there, and I think it's a perfect use case for digital twins. The one thing that I did not really get is when the digital twin is in operation, how is the loop going to look like? What is the information that the digital twin gets from the plant, and what is it sort of suggesting?
Go back. So the digital twin. So at the moment we are dealing with historical data, so it's not really a closed loop. But in the end, it should be that the physical-based simulation model guesses on the basis of the measurement data out of the control system from the gas analytics, because it's an over-data-mined system, back to the input streams. Yes. And so this physical-based solver can figure out the time-dependent fuel mixture. And really, it's not a fuel mixture. It's our 7 lines which fed independent the kiln. But for the simulations, it's a thought fuel mixture. And now we have to figure out with this fuel mixture what kind of combination of the fuels was it. And that is the work for the fuel classification model together with the data-based approaches, where we try by trial and error to find out what combinations of waste streams was it. And we know only the waste codes. Yes.
And what happens with the information about the input? Is it just for information?
So we build up with that a database with so we have now a database with waste codes and also with the supplier which delivers this waste. And normally it is so that every supplier has its field of he's working on. So when a supplier deals with activated carbon, then normally he brings next time again activated carbon. When we be in the same example with the filter materials, as you can say, these are recurring fractions when there come this waste code again from this supplier, and then you already analyzed it, and then you can say, yeah, it will have the same combustion behavior, and can reorder your input streams better to have a more moderate operation and not peaks.
So you use the measurement data to get a better classification of the streams, and then you use this prediction of the streams to improve the control.
Yes, but this is the second step. Yes.
Nice. Thank you. Sophie, do you also have a question?
Yes, thanks for the interesting presentation. you said it, or Felix, I think you said in the end, so it's to improve the control in the end, but also to improve the operation, right? To make it more smooth with less peaks and less changes in, I don't know, flame temperature and flue gas temperature and that stuff, right? I'm not sure about this special waste plants, but for typical household waste incineration, I know that there is a lot of operator knowledge contributing to good conditions, let's say, in the plants. So is that something that happens to you in this project too, that there's a lot of operator knowledge that you have to take into account, or is this not the case for this special waste types, for these also more dangerous waste types than conventional residual waste?
I would say it's the Champions League of waste combustion, which we are speaking here. Sorry, because you don't know what is the waste you're feeding into the rotary kiln. So there is a lot of experience needed to control it. But controlling means in this case so that you don't go in an emergency operation. So you just be reactive, not proactive. To if you see that there is too much temperature, so go more wastewater in it that is cooled down and so on. And when you know in the future more about the wastes you're feeding, and that's the reason why we trying to build up such a database for recurring fractions, then you can be more proactive in the controlling. So if you, I say an example, if you want to have a mixed heating value of 20 megajoules per kilogram, and you know the one has 10 and the other 30, and we do the same amount of it inside, then it fits, yes. And that's a problem because you don't know what it is really. You don't know if it is 5 megajoule or if it's 30, and that's the problem why it's up. Have you these peak loads? Yes.
But in your project, in the model development, there is not too much operator knowledge included, because I think that's also interesting questions, how this specific domain knowledge and knowledge from the practice can be included in such a digital twin or shadow development. But as I understood, it's not too much of that type of background, because it's
when you go to stage 2, this will be more important, I think, because then you are getting attached with the operators, but in stage 1, not that much. But yeah, you're right. Operators are always important to get into the loop. But yeah, you can also see in the measurement data which operator was was in work. So it's quite interesting to have a look on it.
So you don't have only the fuel streams, but also the operators in your model. Okay, thanks.
Werner?
Yeah, so we also saw this, that you can see who was operating, just as a side comment. Have you thought of using also, for example, camera data from the waste that is fed to the system, so that you don't have to be so reactive to things that are going on, and maybe other measurements like, I don't know, kind of humidity or something like this from the waste, or other image data?
There are some plans. In the last year, we got for the barrels RFID tags. So now we know time dependent which waste codes for the barrels which will be fed to the kiln. The biggest black box, when I say it like this, is the bunker, because it's really a problem that you store with a system in a bunker. It's not that easy because there are limitations with the storage volume, and sometimes when some waste comes, it has to be burned now, and it's really challenging. But you're right, there was the idea to make some camera analytics in the bunker, for example, but it's quite challenging because in this environment every camera gets destroyed because there is so much stop and yeah, solid particles. It's quite challenging. Yeah, let's have a look on the future.
Okay.
Nice. I think this question about like image processing and such is a really interesting one, because throughout the presentation sessions we've seen that there was a very strong focus on physics models and some data-driven models, though I think in other areas of AI research and also automatization, you get more of this image processing, well, applying deep neural networks, I think. And I'm wondering whether this is going to be applied in our domain as well in the near future.
I think for this project, it could be interesting because you have a very skilled operator, and they all, most of the time, I would assume they look on some things and they act. So if you could cover this with a camera, it has a high chance to bring you big efforts. But yeah, it's not simple, and it's a lot of data wrangling and so on.
There is one idea for camera analytics, so optical analytics, for the ash analytics, because for in the combustion plants you have to consider that you don't have that much TOC in the ash in the end to dispose it. So it's less than 5%, and you can see it on the color from the ash, because when it's more gray or more black, you see what TOC is in it. So this could be one interesting approach to analyze such a thing like this. Yeah. But we are more on the basic problems now, and yeah, we have to tackle this once first.
Right. Reinhard has a comment.
Yeah, hello. Unfortunately, I just heard the last few minutes of your presentation, but I remember from other presentation that I saw someone who did a prediction of the lower heating value of garbage and waste based on machine learning. So based on weather data, either if it's a holiday or something. Have you looked in this kind of direction already? Maybe I can forward this, because I think they had reasonable results with it.
I'm really interested in it, but I don't know that approach. But yeah, it's like the industrial waste which will be delivered to these systems. I don't know if it's really useful to have a look on the seasonal approach, but yeah,
there was
why not? It's
some funny. So either if it was a holiday or if there was a festival in this town, there was a whole other composition of the garbage, and they were able to predict it some.
So that's sort of the big data approach.
Yeah.
Interesting, yeah.
I will try to look it up where I saw that.
Thank you very much.